Hi friends, I am Meenakshi, student of BSc Chemistry Honors, second year of fourth sem from Pandit Negiram Sharma Government College, Rohtak. Today I am going to read the chapter Chemistry of Lanthanide Elements. We have learnt about the elements in which the last electron enters the f orbital of their atoms are called f group elements. In these elements, the last electron is added to the outermost called anti-penultimate energy level, that is n minus 2. These elements are called inner transition elements because these constitute transition series within transition series. D block elements. These consist of two series of elements placed at the bottom of periodic table. These two series are formed by filling of electron in 4f and 5f orbitals and are called the lanthanides and actinides respectively. The series involving the filling of 4f orbital following lanthanum La, atomic number 57, is called lanthanide series. The elements present in the series are called lanthanides. There are 14 elements in the series starting with cerium Z58 and ending with lutetium Lu Z is equals to 71. The name lanthanide is derived from lanthanum, the first member of the series. These lanthanides are also sometimes referred to as lanthanones. All these elements have closely similar properties and therefore are considered together. The reason for their similar property is that 4f orbital is in which the electrons are embedded in the inner shells, while 5d and 60 electrons which have similar configuration are exposed more to the surrounding because of their similar physical properties. Their separation and identification proved to be very difficult task. The first stage in their separation was to get them as oxides. However, the occurrence of the oxides of lanthanides was very rare. Therefore, these elements have also been called as rare earth elements. Nowadays, the term rare earth element is not used. Their substantial substantial deposits occur in Scandinavia, USA, USSR, and India. General characteristic of the lanthanides. Electronic structure and position in the periodic table. The lanthanides involves a gradual filling of 4f orbital. It may be noted that the energy of the d orbital 5d and the next inner shell f orbitals 4f are closely similar, and therefore the order of filling of 4f orbitals in the atom show quite irregularities. At lanthanum Z57, both 5d and 4f orbitals become stable due to the increased effective nuclear charge as a result of poor shielding effect of 6s electrons. Therefore, it is observed that at lanthanoid the incoming electron enters the 5d orbital and its electronic configuration La Z is equals to 57 is unknown and noble gas configuration 5d1 and 6s2. However, as we move further after lanthanoid, the energy of 4f subshell becomes lower than the 5d subshell. Therefore, the next electron in the cerium enters the 4f subshell. Electronic configuration of cerium is xenon 4f2, 5d0, 6s2. The filling of 4f orbital continues till we reach the ytterbium, in which 4f subshell gets completely filled. It is clear from the figure that some derivations are observed in the regular increasing order, such as 4 EUGD, YB, LU. These are attributed to the stability of half-filled and completely filled F subshell. The first ionization energy are of the order of 560 kJ per mole and second ionization energy are of the order 1150 kJ per mole. These values are quite comparable to alkaline earth metals, especially calcium. Melting point, boiling point. Lanthanides have fairly high melting and boiling points. However, the melting and boiling points do not show any regular trend as we move from lanthanum to titanium in the series. The inspection of table 4.2 shows that the europium and deuterium having unexceptionally low melting and boiling points. These atoms from europium 2 positive and deuterium 2 positive ions are result in weaker metallic bond because of their less than 3 electron per atom in the metallic bonds. The other lanthanide atoms give 3 electron per atom in the metallic bonds. Therefore, melting and boiling points of Europium and ytterbium are low as compared to the value of the other lanthanide elements. Density. The densities of the lanthanides are low, which ranges between 6.7 to 9.74 gram per centimeter cube. However, there is no definite trend in the density value of lanthanide with increase in the atomic number. Europium and ytterbium have unexpected low values. Heat of fusion and heat of vaporization. The heat of fusion and vaporization also do not show definite trends with increase in the atomic number. Electronegativity values. The electronegativity values of lanthanides between 1 to 1.5 are quite close to those of alkali and alkaline earth metals as block elements. These, therefore, lanthanides are expected to form ionic compounds. Electropositive character. Because of low ionization energy, the electronegativity value low ionization energy and the electronegativity values, the lanthanides are electropositive like S block elements. Oxidation state. The common oxidation state of all the lanthanides is plus 3. In addition, some lanthanides show plus 2 and plus 4 oxidation states also. These are shown by those elements which by doing so attain the stable F0, F7 and F14 configuration. For example, CENTB exhibits plus 4 oxidation states. Cerium and terbium attain F0 and F7 configuration respectively when they get plus 4 oxidation state as shown below. EU in europium and ytterbium exhibits plus 2 oxidation states and they get 5 F7 and F14 configuration plus 2 oxidation state as shown below. Lanthanum GD and LU exhibits only plus 3 oxidation states. These elements show plus 3 oxidation states only because by losing 3 electrons they acquire stable configuration of empty, half-filled and completely filled 4f substrates. F F1, F2 and F8 configuration. The stability of these unusual oxidation state may be dependent upon some other thermodynamic and kinetic factors which are of significant importance, but these are less stable than plus 3 state, which is a characteristic of this family. Color and spectral properties. The lanthanides are silvery white, but many lanthanide ions are colored both in solid state and in the aqueous solution. The color remains same even in the change of the anion. Therefore, the colors are the characteristic of lanthanide ions. The color of the ion depends upon the number of unpaired electrons because it has been observed that the ions containing NF electron have almost similar color to those with 14 minus NF electrons. The different ions having NF and 14 minus NF are their colors. However, it has been observed that some di and tetrapositive ions having same number of electrons and stripositive ions do not have same color. For example, Sm2 positive and Eu3 positive have same number of unpaired electrons, but they have different colors. Some other examples are given in the table here. The color of the lanthanide ions arises due to the absorption of light from the visible region of the spectrum, resulting in the electronic transition within the 4f level FF transition. The remarkable characteristic of the spectra of tripositive lanthanide ions is that the absorption bands are extremely sharp lines like bands in the ultraviolet, visible or near infrared region. Many of these bands are line-like and become even narrower as the temperature is lowered. This behavior is in contrast to the absorption bands of daily transition, which have broad absorption bands. The bands of lanthanide ions so sharp that they are used for characterizing the lanthanide ions. The main reason for the very sharp absorption bands is that 4f orbitals lie deep in the atoms of these elements, therefore they are effectively shielded from the surrounding by the overlying 5s and 5p orbitals, and consequently the absorption bands arises mainly from the electronic transition within the 4f levels. Thus the absorption bands show a little dependence on the nature of the ligands. Magnetic properties. All the lanthanide ions, with the exception of lanthanum, lutetium, cerium, and ytterbium, ions are paramagnetic because they contain unpaired electron in the 4f subshell. The ions lanthanum 3 positive, lutetium 3, cerium 4 positive, ytterbium 2 positive electrons. Ytterbium 2 positive, which have 4f0 and 4f14 electronic configuration, are diamagnetic because they have no unpaired electrons. The magnetic property of the lanthanides are different from those of transition elements. As we know, the magnetic moment arises from two types of motion of the electron. The spin motion of the electron around its own axis produces magnetic moment called the spin magnetic moment, and the orbital motion of the electron around the nucleus produces magnetic moment called the orbital magnetic moment. The observed magnetic moment of the substance is due to the contribution of both spin and orbital magnetic moments. In case of transition elements, the magnetic moment mainly corresponds to the spin-only magnetic moment. The formula for the spin-only magnetic moment is under the root n bracket n plus 2. This is due to the fact that the d orbitals are not well shielded from the environment, take part in the bond formation with the ligands. As a result, the d electron of the metal interacts strongly with the ligands surrounding the metal ion, and due to the electric fields of the ligand, the orbital motion of the electron gets restricted, and thereby the orbital movement of the electron gets quenched. The magnetic moment of deep lock elements thus arises mainly from the contribution of spin motion of electron only. The spin only magnetic moment is given by the formula I have told you earlier. When where n is the number of unpaired electrons, this relationship gives almost correct value of the magnetic moment of the d block elements. However, the above relationship is not valid in the case of f block element. In these elements, 4f orbitals are well shielded from the surrounding by the overlying 5s and 5p subshell. As the result, the electric field of the ligand surrounding the metal ion does not restrict the orbital movement of the electron. Thus, orbital contribution is not quenched. Therefore, the magnetic moments of the lanthanide ions is due to the both electron spin and orbital motion of the electrons. This may be calculated from the relation mu is equals to under the root 4s bracket s plus 1 bracket close plus l bracket l plus 1, whereas s is the resultant spin quantum number and l is the resultant orbital moment quantum number. The theoretical and experimental observed magnetic moment values are given in the table. The magnetic moment of the lanthanides depend upon the atomic number and the number of unpaired electrons. For ions like xanthanum 3 positive, Gd 3 positive, Lu 3 positive, the magnetic moment corresponding to the spin only value. For these configurations, there is no orbital angular moment. L is equals to 0. The above expression become mu is equals to 4s bracket s plus 1 bracket close, and the magnetic moment may be calculated only on the basis of spin only value. Here s is equals to ns, where n is the number of unpaired electron and s is the spin quantum number. For F0 and for F14 configuration, there are no unpaired electron and n is 0. Their magnetic moment is 0 diamagnetic. For 4F configuration, the magnetic moment can be calculated on the basis of spin only value because orbital angular moment is 0. The magnetic moment of tripositive lanthanide ions are plotted in the figure. Lanthanum 3 positive, lutetium 3 positive are diamagnetic non-paired electron. It is observed that the value increases up to neodymium and then decreases to 1.472 Sm3 positive ion. The increase again and reaching the maximum value for the dyspo, dysprosium and holomium. Thereafter, it starts decreasing and becomes 0 for lutetium, which is diamagnetic. Ionic radii and lanthanide contraction. We know that as we move down the group, atomic size normally increases. This is mainly due to the additional shell or the electron between the successive periods. However, as we move across the period from left to right, atomic size decreases. This is attributed to the increased effective nuclear charge, as a result of which the outermost shell of the electron is attracted more and more. Consequently, the size decreases. For example, the covalent radii of alkali metal increases from lithium to cesium, and for halogen, fluorine to iodine. If we consider the ionic radii of the lanthanide, we get very interesting observation. For comparison's sake, we can take the ionic radii of the trivalent ion M3 positive, which are most stable. These are shown in figure 3. It is clear that the ionic radii decreases from one element to another in the lanthanide series, but the decrease is very small. It has been observed that for cerium 3 positive Z58 to lutetium 3 positive Z71, the ionic radii decreases from 1.03 angstrom to 0.86 angstrom. Obviously, for an increase of atomic number 14, the decrease in the ionic radii is only 0.17 angstrom. This is very small decrease in the comparison to the element of the other group and period. Similarly, on moving from cerium to lutetium, the atomic radii also decreases from 1.65 angstrom to 1.56 angstrom, and the decrease is only 0.09 angstrom. This small and steady decrease in the ionic or atomic sizes of the lanthanide elements with increase in the atomic number is called the lanthanide contraction. Cause of lanthanide contraction. In the lanthanide series, the 4f electrons are being added one at each step as we move from one element to other. The shielding of one f electron by another from the nuclear attraction is quite weak due to the shapes of f orbitals. The nuclear charge, however, increases by 1 at each step. Hence, with increasing atomic number and nuclear charge, the effective nuclear charge experienced by each 4f electron increases. Hence, the inward pull experienced by the 4f electron increases, and this causes a reduction in the size of atom or ion. The sum of the successive reduction give the total lanthanide contraction. Consequently, the lanthanide contraction has very significant effect on the relative properties of the elements which precede and which follow the lanthanides in the periodic table. Some important consequences of the lanthanide contraction are given below. Steady decrease in the size. There is a regular decrease in the ionic radii of the lanthanides. Electronegativity. There is a slight regular increase in the electronegativity of the trivalent ions. Electrode potential. There is a small but smooth increase in the standard electrode potential value for the process. Resemblance of the second and third transition series. The lanthanide contraction affects the chemistry of second and third transition series. As we see the table 8, there is a regular increase in the size from scandium to deuterium to lanthanum. Similarly, as we accept normal increase in the size in the group other groups as titanium to zirconium to hafnium, vanadium to niobium to tantalum. However, after lanthanides, the increase in the radii from the second to third transition series almost vanishes. The pair of the elements zirconium, hafnium, niobium, tantalum, molybdenum, tungsten are almost of the same size. The property of the elements are very similar. Similarity among lanthanides. Because of very small change in the size of the lanthanide ions in the lanthanides, the chemical properties are similar. Therefore, their separation become very difficult. Recently, methods based on the repeat fractional crystallization or the ion exchange techniques, which takes the advantage of slight difference in their property like solubility, complex ion, which formation, hydration, etc., arising from very slight size difference of their trivalent ions have been used. Basicity differences. Due to the lanthanide contraction, the size of lanthanide ion decreases regularly with increase in the atomic number. As the result, decrease in the size, the covalent character between the ions and OH negative ion increases, and therefore the basic strength of the hydroxide decreases with increase in the atomic number. LaOH3 is the most basic while LuOH3 is the least basic with increase in the atomic number. The basicity differences in the lanthanides are reflected in increasing tendency to get hydrolyzed due to the decrease in the basic character. There is a slight increase in the degree of hydrolysis in the solution from lanthanum to platinum. Lanthanum 3 positive ions are less readily hydrolyzed than platinum 3 positive ions. Thermal decomposition of oxysalts. More basic oxysalts decompose less readily. LaNO33 decomposes with difficulty and is stable, whereas LuNO33 is unstable and decomposes readily. Solubility of salts. Lanthanide hydroxide precipitate at regularly decreasing pH value from lanthanum 3 positive to deuterium 3 positive. Example LaOH3 at 7.83, GDOH3 at 6.83, Lu3 positive at 6.30. The sizes of YB ytterbium, HO and DY. Due to the lanthanide contraction, the radii of ytterbium 3 positive is comparable to the heavy lanthanides TB, EY, HO and ER. Therefore, they occur together in the natural minerals. Reactivity of lanthanides. All the lanthanides are highly electropositive metals and have almost similar chemical reactivities. This is due to the fact that the lanthanide differ only in the number of 4f electrons. Since these electrons are very effectively shielded by the interaction with other elements by the overlying 5s, 5p and 6s electrons, they show very little difference in the chemical reactivity because of their similar chemical reactivity. Their separation from one another is very difficult. Lanthanides are in general are more reactive than deep block elements. Some of their chemical characteristics. They tarnish readily on exposure. on exposure to air in finally divided state, but all bonds in air to form sesquioxide of the formula Ln2O3, where Ln stands for lanthanide, except cerium, which gives CeO2. Ytterbium, however, resists the action of air even at 1000 degrees Celsius due to the formation of protective coating of its oxide. All react with water slowly in the cold but rapidly on heating, liberating hydrogen and forming LNOH3. All these combine with hydrogen at 200 to 300 degrees Celsius, giving LNH3. They also combine with halogen, oxygen, and sulfur. They act as a strong reducing agent for oxides of other metal. Cerium is used as a sponge of oxygen and sulfur in many metals. They react with nitrogen to form nitrides of formula LNN. Solubility of compounds. The fluorides, oxides, hydroxide, carbonate, phosphate, chromates, and oxalates of the lanthanides are largely soluble in water. On the other hand, halides other than fluoride, nitrate, acetate, percolates, and salts of oxoacids of lanthanide are soluble in water. The solubility behavior of the salt of lanthanide follows the pattern of solubility of salt of the group 2 elements. However, lanthanide sulfate, unlike the sulfate of the group 2 elements, are soluble in water. Tendency to form complexes. Although lanthanide ions have a very high charge 3 positive, yet they have large size of their ion compared to the transition metals. As a result, they have low charge density and therefore they have very less tendency to form complexes. Their complexes with unidentate ligands are very few and form complexes with fluorine and oxygen donor ligands. However, they form a complex with a few chelating ligands such as beta diketones, oximes, and ethylene diamine tetraacetic acetic acid EDTA, alpha alpha dash dipyridyl, and hydroxycarboxylic acid such as citric acid. These complexes usually have high and variable coordination number, and the water or solvent molecule are often attached to the central metal atom. Beta diketone complexes of EU and PR dissolved in the organic solvent are used as a lanthanide shift reagents in the NMR spectroscopy. In contrast to the transition element, the coordination number is not very common. Coordination number below 6 is also uncommon and occurs only with bulky ligands such as 2,6-dimethylphenyl and NSIM3 bracket 2 ligands. However, coordination number 7, 8 and 9 are common, and give give a variety of stereochemistries. For example, the coordination number of LnO2 N3 positive in aqueous solution are thought to be 9 for early lanthanides and 8 for the later smaller member of the series. However, these ions are highly reliable. The smaller ytterbium ion YB3 positive forms 7 coordination complexes, and larger La3 positive is 8 coordinated in LAACA3O2 2, where ACAC is acetyl acetone. The structure of these complexes are a capped trigonal prism and the square antiprism shown below. The coordination number 10, 12 occur with large lighter lanthanide and small chelating ligands NO3 negative, SO4 2 negative. Cerium 4 positive is smaller and highly charged and forms SCeNO3 6 2 negative in the non-aqueous solvent N2O4. This is 12 coordinated cerium in which each NO3 negative ion uses 2 oxygen atoms to coordinate to the metal. Where two transnitrates of the complexes are replaced by PH3PO, it gives the 10 coordinated orange color neutral complex. The sulfates CeSO42NH2O, where N is 0, 4, 8, 12, and NH42CeSO4 thrice, and iodates are also known. Large number of salt of organic acids such as oxalic, citric, and tartaric acid have been studied mainly for the separation methods. These anions have chelating oxygen ligands forming complex with Ln3. Unidentate oxygen donors such as pyridine and oxide and triphenyl phosphine oxide also form many complexes with lanthanides in plus 3 oxidation state. Complexes with ligands such as En, diene, bipi, and terpi can also be prepared in the polar organic solvents. For example, coordination number of 8, 9 and 10 as in Ln En4 3 positive, Ln taupi 3 positive, Ln diene 4 NO3 2 positive are typical examples. As with other transition metals, the lanthanides can be induced to form complexes with exceptionally low coordination number by use of the bulky ligands such as N-SiMe3 2 negative. This is an example of coordination number 3, which is the lowest found in the lanthanides. They are volatile, air sensitive, easily hydrolyzed. They are planar in the solution but pyramidal in the solid state. With pH 3PO, the coordinated distorted tetrahedral adducts are formed. Lanthanides also form two main types of organometallic compounds, predominantly ionic cyclopentadienides and alpha bonded alkyls and aryls. These types of compounds are usually thermally stable but unstable with respect to water and air. The series LnC5H53 and LnC5H52Cl are the salts containing C5H5 negative anion and are readily prepared by the reaction of anhydrous LnCl3 and NaC5H5 in appropriate molar ratio in THF. In polar solvent, these complexes are solvated and are monomeric, but in non-polar solvent, the tries C5H5 compound are insoluble, while by C5H5 compound dimerized. The lanthanides also form alkyls and aryls by the metathesis in THF and other solutions, ether solutions. LnCl3 plus 3 LiR gives LnR3 plus LiCl. LnCl3 plus 4 LiR gives Li LnR4 plus 3 LiCl3. Triphenyls are polymeric in which Ln is tetrahedrally coordinated to 4 alphyryl groups. Methyl derivatives have also been obtained. Octahedral Ln Me6 3 negative species of lanthanides have been isolated. In contrast to the transition elements, the lanthanides do not form complexes with pi bonding ligands such as CO, NO, CNR, etc. The differences arise because the 4F orbitals are well shielded and are inside the atoms. Therefore, they cannot take part in the pi bonding, whereas in the transition elements, the d orbitals are commonly involved in pi bonding. Double salt formation. The lanthanide salts form double salt with corresponding salts of ammonium alkali metals. Double salts like alums with 24 water molecules are not formed. This is because the lanthanide ions are so large that they cannot coordinate to 24 water molecules octahedrally as in alums. Occurrence of lanthanides. Although lanthanides are originally called rare elements, the recent studies have shown that these are not rare. All the lanthanides except promethium occur naturally. Some of them, particularly cerium, lanthanum, and neodymium, are very common, occur in fairly large quantities. Cerium is 26th most abundant of these elements. It has been observed that lanthanides having even atomic number are more abundant than their neighbors with odd atomic number. Methods for separation into individual elements. The properties of metal ions are determined by the size and charge. All the lanthanide ions are trivalent and have almost same size, so that the properties are almost identical. Therefore, the separation of lanthanide from one another is very difficult. Recently, methods based on the repeated fractional crystallization, ion exchange technique, etc., which take advantage of slight difference of the property like solubility, complex ion formation, hydration arising from the very slight size differences of the trivalent ions have been used. These methods are discussed below. Repeated fractional distillation. Simple salts like of the lanthanides such as nitrate, sulfate, bromate, oxalate as well as double salts form well-defined crystals. The solubility of the salt decreases from lanthanum to lanthanum 2, and therefore by repeating fractional crystallization a number of times the individual component can be obtained. During fractional crystallization, the less soluble salt will obtain first and the more soluble will be obtained at last of all. By repeating the crystallization process, the less soluble salt will accumulate more and more in the crystal and mother liquor, which contain more and more soluble salt. This is the method how now have been improved by the use of non-aqueous solvents such as ether. Fractional precipitation. When only a small amount of precipitating agent is added to the mixture of lanthanoid salts, the substance having the lowest solubility product will participate most rapidly and most completely. For example, if sodium hydroxide is added to the solution of lanite nitrates, which is the weakest base and has the lowest solubility product, a precipitated first while LaOH3, which has the highest solubility product, is precipitated last. A partial separation takes place in the manner by redissolving the precipitates and then precipitating again a number of times. It is possible to have complete separation. Solvent extraction. The partition coefficient of a salt of these metals between water and organic solvent are slightly different. Therefore, these can be extracted by using different solvents and repeating the extraction process again and again. For example, the partition coefficient of the GDNO33 between the water and the normal butyl alcohol is 1.06 times greater than that of LaNO3. This means that the GDNO33 can be separated from LaNO33 by the continuous extraction with water from solubility to these salts in the butyl alcohol. Change of the oxidation state. Some of the lanthanides show +2, +4 oxidation state in the addition of +3 and +4, which is the most characteristic of the lanthanides. The property of the M2 positive M4 positive ion are different from those of the usual M3 positive ion. For example, cerium can be separated from a mixture of trivalent ions of all lanthanides by oxidizing its cerium to cerium 4 positive state. By reacting it with the alkyne KMnO4, C4 ion has a greater charge than C3 positive ion. Therefore, it is smaller and less basic, less soluble. It can be precipitated as CeOH4 by the addition of small amount of alkali, leaving all trivalent lanthanides in the solution. Similarly, europium can be separated from the mixture of trivalent lanthanide ion by reducing it to the first 2 plus 2 state by zinc amalgam, and Eu plus 2 positive can be precipitated as EuSO4, which is insoluble in water. The sulfates of all the trivalent lanthanides, on the other hand, are soluble in water and remains in the solution. Thermal decomposition. When a mixture of lanthanide nitrate is fused along with some alkali metal nitrates, a temperature is reached when the least basic nitrate changes to oxide. Therefore, heavier nitrates decompose first while light lanthanide nitrate decompose at last of all. Therefore, the process of decomposition of nitrates is different at different temperatures is carried out, and the oxides separated at each stage are then dissolved in an HNO3. There are about 100 minerals known to contain lanthanides. The main minerals are monazite. It is the most abundant, most widespread mineral, accounts for about 78% of the lanthanide mines. It is the mixture containing La phosphate and trivalent phosphate of the lighter elements such as cerium, Pr, and D. Also contain small amount of heavier elements, thorium phosphate. These minerals are contaminated with such as similarly concentrated minerals such as ilmenite, FeTiO3, and cassiterite, SnO2. Monazite occur in southern India, South Africa, Brazil, Australia, Malaysia, etc. Bastanite. Bastanite. It is a mixed fluorocarbonate M3CuO3F, where M is lanthanide, The distribution of the metal in monazite and bastanesite is almost similar, but the difference is that monazite contain about 5 to 10% of thorium oxide and 3% of deuterium, heavier lanthanide earths, which are virtually absent in the bastanesite. Large amount of bastanesite minerals are found in California, Sweden, New Mexico. Cerite. It contains silicates of CeLaPr and DSM. It is found in Norway and Sweden. In addition to both main mineral, many other minerals are small in amount. Euxenite containing Ce and Bth deuterium earths. Crythite containing double silicates of cerium. Xenotime containing yttrium Th. Gadolinite containing ytterbium or CETH. Isolation of lanthanides. Monatite is the best known mineral containing the lanthanide. It is a mixture of phosphate LnPO4 containing thorium, zirconium ion, and titanium as silicates. The mineral is powdered and digested with low concentrated H2SO4 until a paste is obtained in which the phosphonates containing into the corresponding sulfates. The paste is separated by centrifugation and treated with cold water. The sulfate, being more soluble in water than in hot water, pass into the solution, while silica, zircon, being insoluble, are precipitated out as phosphate. Then the solution is treated with sodium sulfate, which precipitate lanthanum and light lanthanides as small as double salt, which while the heavy lanthanides still remain in the solution. The precipitated double salt of the light lanthanide are treated with hot sodium hydroxide solution. When they are converted into a mixture of oxides and hydroxide, the mixture is washed to remove the sodium sulfate formed during the process and dried in the air at 100 degrees Celsius. As oxides in this process, cerium is completely oxidized to cerium O2. Cerium 3 positive, cerium 4 positive, and other lanthanides are charged as oxide Ln2O3. The mixture is treated with dilute HNO3. So the lanthanide oxides accept CeO2 dissolved. The CeO2 is left as residue and is filtered. The crude CeO2 is dissolving in 45% HNO3 and added to an excess of dilute H2SO4, whereby the cerium is precipitated as a red basic nitrate CeOH. The components NO3 3H2O. After the removal of Ce, the other light lanthanides are separated into individual complex by components by different methods based mainly on the solubility differences. Ion exchange method. This is the most successful, most efficient method of separation of lanthanides. Generally, the column of synthetic ion exchange resins with acid functional groups such as CO2SO3H is used. The solution containing the trivalent lanthanide ion is passed through the column when the hydrogen ions are replaced by the metal cations. The column now contains the lanthanide ion fixed on the resin. In the other, to recover them, the column is eluted leached with citric acid ammonium citrate solution. In the first phase, the ammonium ions replaces the lanthanide ions. The ions which are bound least firmly to the resins are displaced eluted by the ammonium ion first, while those which are bounded most firmly are displaced last. The firmness with which lanthanide ions are fixed to the resins depend, depends upon the size. That is, smaller the size of the lanthanides ion, the more firmly it is bound to the resins and vice versa. Since lanthanides ion are present at the hydrates, the firmness depends upon the size of the hydrated ion. Smaller ion is hydrated to the greater extent, therefore the smallest lanthanide ion Lu3 positive will be the most heavily hydrated, while lanthanum 3 positive ion being the largest will be hydrated to the minimum extent. Hence, The size of the hydrated La3 positive ions is the smallest and therefore it is attached to the column with maximum firmness. On the other hand, Lu3 positive ions are attached with minimum firmness and firmness decreases from lanthanum to titanium. Thus, Lu3 positive ions is eluted first while the La3 positive ions are eluted last. By complex formation, lanthanide oxalates are insoluble in water but they can dissolve by complexing with ethylene diamine tetraacetic acid. These complexes differ in the stability toward acids. The least stable complex is destroyed first, changes to the oxalate while the most stable complex is destroyed last on addition of an acid. Production of metals. Electrolysis of the fused chlorides. The method is similar to that used for the preparation of calcium by the electrolysis of calcium chloride. The electrolysis of CEO2 in the fused CeF2. This method is used in the production of cerium and is similar to the method used in the metallurgy of aluminium. Reduction of anhydrous chlorides with sodium. The reduction takes place at the higher temperature above 1000 degrees Celsius. This method is used for the production of lighter lanthanides such as La, Ce, and Ca. LaCl3 plus 3Na at 1000 degrees Celsius gives La plus N3NaCl. Reduction of anhydrous fluorides with calcium and magnesium. This method used in the production of heavier lanthanide because of the anhydrous fluoride are non-hygroscopic and less volatile than the chlorides. The loss by evaporation is therefore small when fluorides are used instead of fluorides. The reduction is carried out at the temperature above the 1000 degrees Celsius. Lanthanide compounds. The lanthanides are soft, silvery, white. They are electropositive and therefore they are very reactive. They react with hydrogen forming hydrides of composition LnH2, LnH3. These also react with several other known metals included oxygen, halogen, sulfur, nitrogen, phosphorus, carbon, silicon, etc. Most of the lanthanide compounds are known in plus 3 oxidation state. However, some compounds of lanthanide in plus 2 and plus 4 oxidation state are also known. The important lanthanide compounds are discussed below. Compounds in plus 3 oxidation state. This is the most common oxidation state of lanthanides. Oxides. All the lanthanides tarnish readily in air. These burn with oxygen forming oxides Ln2O3. These are also obtained by the ignition of hydroxide carbonates. Nitrates Ln2O3 are well characterized. Lanthanide oxides absorb water, carbon dioxide from the air to form hydroxides and carbonates respectively. Therefore, the lanthanide oxides Ln2O3 are strongly basic and their basic character is decreased as atomic number increases. For example, La2O3 is strongly basic while Lu2O3 is least basic. The lighter most basic oxide resemble the oxide of group 2 elements. All are soluble in water but absorb it to form hydroxides. They dissolve readily in aqueous acid to form solution which contain the LnH2OX3 positive ions are provided. They are kept on the acid side of pH 5 to prevent hydrolysis. Hydrous hydroxides can be precipitated from these solution by the addition of ammonia or aqueous alkali. Ln2O3 adopt three types of structure: A type, B type, and C type. Hydroxides. The lanthanides react slowly with cold water but more rapidly on boiling with liberation of hydrogen and form the corresponding lanthanides hydroxides. The hydroxides can also be prepared by adding dilute solution of sodium hydroxide at solution containing lanthanide 3 positive ions. The hydroxide are precipitated as a gelatinous precipitates. These are ionic compounds and are basic. Lanthanide hydroxide are less basic than CaOH2 but more basic than AlOH3, which is amphoteric. The basic character of lanthanide hydroxide decreases with increase in an atomic number along the series. Therefore, LaOH3 is most basic while LuOH3 is least basic. This is due to the lanthanide contraction. Chalcogenides. Chalcogenides of similar stereochemistry to the oxides are known to form many lanthanides. In general, these are stable in dry air but are hydrolyzed in the presence of moisture. If heat is heated in air, they oxidizes to basic salts of corresponding oxoanion and they show varying susceptibility to attack by acid with evolution of H2Z. Halides. Lanthanides on oxidations in oxidation state 3 form trihalides. Anhydrous lanthanides fluorides are prepared by adding HF solution to a salt solution containing Ln3 positive ions. The fluorides are very insoluble, therefore are easily precipitated from their solution by HF or NaF. However, with excess of F negative, the fluorides of heavier elements, lanthanides may form soluble complexes. Anhydrous lanthanide fluorides are prepared by heating the metal in the atmosphere of dry chlorine or by heating lanthanide oxides with carbonyl chlorides. The chlorides are deliquescent non-volatile solid. These are soluble in water and crystallize with 6 or 7 molecules of water of crystallization. It may be noted that the simple anhydrous lanthanide halides cannot be prepared by simple heating of hydrated salt as they form lanthanum oxochlorides instead of dehydrating of two anhydrous halides. Anhydrous halides can also be prepared by heating the oxides with appropriate ammonium halides. The aqueous solution of other trihalides are prepared by dissolving the oxides or carbonates in the aqueous HX and hydrated having 6 to 8 H2O molecules can be crystallized. Anhydrous trihalides can be prepared by thermal dehydration or these hydrates of lighter lanthanide, bromides and iodides are more susceptible to hydrolysis. Nitrides. At high temperature, the lanthanide react with nitrogen to give nitride of the formula LAN. It gets hydrolyzed by water like aluminum nitride ALN to give the corresponding hydroxide with liberation of ammonia. Oxosalts of lanthanides. A large number of oxosalts of lanthanide are known. These include carbonate, nitrate, sulfate, oxalate, phosphate, and perchlorates. These are generally prepared by dissolving the lanthanide oxide, hydroxide, or carbonate in the corresponding acids. Double salt of lanthanide. Lanthanide sulfates are known to form double salts with ammonia and alkali metal sulfates. It may be noted that a double salt in case of elm are generally associated with many as 24 water molecule of crystallization. However, the double salt of lanthanide cannot be associated with as many as 24 water molecule of crystallization. This is because the lanthanide's ions are too large to coordinate with 24 water molecules of crystallization octahedrally as in elm. Compounds in plus 4 oxidation state. Among the lanthanide, only cerium, parasiodium, dymium, neodymium, terbium, dysprosium show plus 4 oxidation state. The only lanthanide which exists in plus 4 oxidation state in the solution and has an aqueous chemistry in Ce4 positive. The cesium 4 positive solution are expensively used as a versatile oxidizing agent in the volumetric analysis. TB4O7 under extreme condition, for example PrO3 is obtained by O2 at 282 bar and 400 degrees Celsius while TbO2 requires atomic oxygen at 450 degrees Celsius. Among the stable halides of the lanthanides, in plus 4 oxidation state, only fluorides of cerium 4, Pr4 and Tb4 are known. CeF4 is comparatively stable and can be prepared either directly from the elements or by the action of F negative on the aqueous solution of cerium 4. When it crystallizes as monohydrate, it can also be prepared by treating cerium 3 fluoride with fluorine at room temperature. It is a white compound rapidly hydrolyzed by water. The other tetrahalides are thermally unstable. They can only be prepared dry because they oxidized as water. Tb4 can be prepared from Tb3 and F2 at 300 degrees Celsius. Parasiodium 4 fluoride PrF4 can be prepared by fluorinating a mixture of NaF and PrF3 with fluorine to form Na2PrF6. Then NaF is extracted from the reaction mixture with liquid HF. Compounds in plus 2 oxidation state. The compounds in the common lanthanides showing plus 2 oxidation state are neodymium, samarium, europium, terbium, deuterium, europium yttrium display plus 2 oxidation state because they acquire stable F7 and F14 electronic configuration respectively. Attempts to prepare lower oxides of formula LNO have been made, but only NDO, SMO, EUO, YBO have been obtained. The most stable divalent lanthanide is EU2 positive and its chemistry is well studied. It is stable in water, but its solution is strongly reducing. EU2Cl2 can be prepared as a solid compound by reducing EU3Cl3 with hydrogen under reduced pressure. Aqueous EU3 positive solution can be reduced by magnesium, zinc amalgam, and or electrolytically to give EU2 positive. EU2SO4 can be prepared by electrolyzing EU23SO43 solution. When the divalent sulfate gets precipitated, EuH2 is ionic and similar to CaH2. The chemistry of EU2 resembles the chemistry of calcium in many ways. For example, the sulfate of both are insoluble in water. The dichlorides of both are insoluble in strong HCl. Both the metals are soluble in liquid NH3. Thank you.